you doing, stupid?
Hi, my name is Sarah.
I'm Stephanie.
I'm Sydney.
And I'm Hannah.
Today we're going to be talking about is your shut eye keeping you safe in traffic?
So our research question is, do hours of sleep have an effect on an individual's likelihood to be involved in traffic accidents? So our official claim is that sleeping out fewer hours per night may be linked to a higher likelihood of being involved in traffic accidents. And so with that claim, our two variables are hours of sleep and then the amount of traffic accidents. And we predict a negative relationship between the two. So more sleep would be less likely or less accidents, and less sleep would be more accidents or more likely to have more accidents. So defining variable one, our conceptual definition for hours of sleep is how much time in a 24-hour period does a person spend asleep. We can operationalize that a few different ways. But it could be like the average hours slept per night over some period of time. So it could be 6 months, 1 year, or we could measure sleep with certain like measuring tools. It would depend on sort of like the reach of the study that we actually did. In our measurement method, it would be a self-report or like I said, like a Whoop or Apple Watch, something like that. And then for the scale of measurement, we'll use interval because it's unlikely that many people would have like a true 0 hours of sleep. Like usually people sleep at least some. So we would do interval scales, something like 0 to 3, 3 to 6, 7 to 9, and then 10 or greater. Our second variable would be number of traffic accidents. And we conceptually define that as an individual's frequency of being involved in any type of traffic problems. So that can include like serious crashes, fender benders, like anything that would be on a record, basically. And we operationalize that as an individual's self-reported number of traffic accidents experienced in a certain time frame that would match the time frame of the sleep. So we can do 24 months, 1 year, 6 months. It would depend on the specific study. And then our measurement method, we self-report. And then we could also back up the self-report with pulling data from stuff like the DMV or other like public records. And then for this one, we'll use a ratio scale because it is likely that we would have a true 0 because some people don't be involved in traffic accidents.
So for variable one, I wanted to use face validity, and I feel like our variable one measures exactly what we want, which is to know how much sleep an individual is getting at night. And by asking how many hours or using a sleep tracker, it can lead to straightforward answers. And it involves no confusion or indirect measurements, so that's why face validity is accurate for this variable. And then for variable two, it's kind of the same thing. It measures exactly what we want, which is the probability of any individual being in a traffic-related accident. So we can get this through self-reports or official records like police reports or like insurance records. And these are great methods of measurement, which also don't have any confusion or misleading information. And we can also do test retest to use, we can use test retest for further like accuracy on the self-reports.
So for our first variable, we're focusing on criterion validity, which examines whether our measure, so in this case, average hours of sleep, can accurately predict a meaningful real-world outcome. The real-world outcome we're looking at is the number of traffic accidents a person has reported in the past 12 months. So like Hannah said, this could be like big, multiple cars or just little fender benders, anything of that sort. But to test this, we would collect like we mentioned, self-reported data or official records from sources like the DMV or police reports for each participant. Then we would create a scatter plot with average hours of sleep as the x-axis and the number of traffic accidents on the y-axis. So if a measure shows good criterion validity, then we would expect to see a negative correlation, meaning that as average hours of sleep increase, then the number of traffic accidents reported would go down. And then for our second variable, again, still focusing on criterion validity, but this time our measure is the frequency of traffic accidents. So we want to see whether this measure accurately predicts a real-world outcome, such as, for example, like increase in insurance premiums or driver's license penalty points, just a few examples. And to test this, we will collect data on each participant's number of accidents within a set time frame, like 24 months is just one example, along with either their current insurance costs or the number of penalty points that they have received. Then we would plot this information on a scatter plot with the number of traffic accidents on the x-axis and either insurance premium or penalty points on the y-axis. And unlike our first variable, we would expect to see a positive outcome here. So the more accidents, the higher insurance rates or more penalty points, which would confirm that our measure of accident frequency reflects meaningful real-world consequences.
For reliability of variable number one, we thought retest reliability is the best fit for this measure. And it's important because it will help provide direct answers from the individual, as well as consistent evidence for claims regardless of how many times the question has been asked. And it also protects the study from measurement error and strengthens internal validity. So this is a scatter plot, and it shows a high reliability, and it's the retest for hours of sleep. And it shows high reliability because it is consistent across both test measures, and people report the same information on the first test as the second one. And for statistical validity, we expect a moderate and negative effect size between the two variables, since sleep deprivation can lead to exhaustion and impaired attention, which can cause car accidents, but it is multifactorial. So weather and traffic are like leading for car accidents, and it makes lack of sleep just a small contributing factor. And then for potential outliers and curvilinear trends or range restrictions, some potential outliers could be people who report extremely low or high hours of sleep, as well as a high number of accidents annually. And while we expect a linear negative relationship, there could be curvilinearity by using a regression model, which is what we could use to look for that. And with many reports of similar hours of sleep, the restricted range would reduce the correlation. And to make sure this doesn't happen, we would aim for a diverse sample of individuals with different sleeping hours to capture full variability. And for internal validity, we could explain why internal validity cannot be established. This correlation study, with and without many experimental control or random assignment, we cannot rule out alternative explanations for this relationship. And for the third variable, to explain the relationship, a likely third variable would be stress, which can reduce the sleep, increasing the chances of driving errors or accidents. And three causal criteria are covariance, temporal precedence, and internal validity. And covariance are met, but we do not meet temporal precedence or internal validity, so causation cannot be claimed.
Okay, so for external validity, our sample population, or our sample refers to the specific group of people that we collected data from. So this could either be like 1,000 licensed drivers recruited through DMV records, driving schools, online surveys, or even a university population, but our population is all licensed drivers. So the settings and context that this would apply would be, we want to go across different settings. So we could compare night or shift workers to day workers, because like we talked about, sleep, huge impact, urban versus rural drivers, or considering differences in driving environments like weather, season, and as we talked about, like traffic, distance traveled. And finally, for the limits of generalizability, few examples for this would be sampling bias. So just if our sampling isn't representative of all drivers, that could be an issue. As well as differences in how sleep and accidents are measured, and specific contextual factors like regional driving laws or road conditions. And these limits like remind us to be careful about how broadly that we apply our results.
So connecting to published research, for this one we chose a meta-analysis, because we thought that would be a good way to, like a starting point to assess all of the studies that are similar that have already been done. So ours is titled Sleepiness, and the Risk of Road Traffic Accidents, a systematic review and meta-analysis of previous studies. And this one showed a very high level of evidence that sleep deprivation and driving do have that negative relationship. And some of their data showed that that drowsy driving due to lack of sleep can increase the probability of a road crash involvement by 1.29 to 1.34 times higher than driving without sleepiness. And those specific things, the 1.29 came from a fixed effect model, and then the other one a random effect model. And they both had very narrow 95% confidence intervals, neither of them including 0. And the first one, the 1.29 times higher, has really just like a 0.1 range. So that's showing a very strong statistical validity there.
So how we work together, it's similar to the first project we did. We divided responsibilities on Zoom, so we got together and we chose which slides we wanted to work on. The resources we used were mostly the class slides, the book, Google Scholar, and ChatGPT. AI was used to create things like the scatter plots. It's a great tool to help portray our data in a necessary chart. And we did this by giving it a prompt that followed our data, like create a scatter plot of our two variables that show high retest reliability. And we made sure it aligned with the class content by comparing it to our slides and the textbook.